Hello, welcome back. I'm Professor Steve Miller. Today we'll return to our module on oblique shock waves. First, we'll look at shock detachment. That's the case, of course, where the shock has detached from the turning angle or the particular vehicle or plane of symmetry, and it's moved upstream. This is where, of course, we do not have particular solutions of the theta-beta Mach number equation. Then we'll look at particular three-dimensional shocks, at least through figures, and briefly talk about their solution approach. Then we will look at a number of figures and diagrams and charts, which of course we've provided through the class handouts and the charts provided from NASA Ames Research Center, which we lovingly call the Ames tables. Let's get started. In this particular image, we see one projectile going down our ballistics range with a high-speed Schlieren image taken as it passes. You can see a reference line in the frame right here. This black part of the image, of course, is the projectile, and it moves from right to left. We can see in the Schlieren an undisturbed median, which is going to be compressed greatly and quickly through this very strong detached oblique shock wave. Of course, the turning angle of this vehicle you might view as 90 degrees, which never has any solution of any particular set of theta, beta, and Mach number equations. This causes the shock to offset from the vehicle in front of it. So in this particular case, we might ask ourselves, how do we solve this problem? And it might be seen as rather difficult. Nonetheless, the flow moves from the shock, and it's subsonic in this region, as it's behind a rather normal shock, and it transitions and becomes supersonic as it moves around the vehicle, and we see a number of lines. And these, of course, are Prandtl-Meyer expansion waves, which we'll talk about in the next major module of this class. We then see flow separation in a large and strong, very compressible, turbulent wake behind the vehicle, which is like this granulated material. We also see a number of shocks and expansions coming off the material because, of course, the turbulence, that is, because, of course, this is a supersonic type shear layer. So we have supersonic flow on this side of the flow, and in the turbulent wake, it's very likely subsonic and some recirculation happening. We'll try and look at this particular image further. Here's another simple Schlieren, but in this time it's a cylinder in a wind tunnel, and the flow moves from left to right instead of the projectile or object in the fluid moving from right to left. Once again, we see almost the same type of flow physics. We see a bow shock, some transition to supersonic flow, which is much cleaner than the previous case. And then we see another shock wave where the flow is separating off the cylinder here just before that in the turbulent wake. And once again, we get all these types of supersonic flow phenomena downstream of this weaker oblique shock, which is attached to the vehicle, unlike the oblique shock, which is the bow shock in this case in front of the vehicle. Indeed, simple solutions of the shock equations exist, as we found previously in our charts and tables and equations, and it's very straightforward to find them if, of course, they're planar and attached. Now, unfortunately, if the body is blunt, like in these two examples I just showed, or the deflection angle or the turning angle is greater than particular theta max for a given incoming Mach number locally before the shock wave, then of course the oblique shock will detach, as we showed previously. And it could form, say, in reflection, like a lambda shock or normal shock attached to the wall, or it can move and be attached in front of the vehicle, like we see here, or it could be attached to the wall, but in front of the corner, as we showed in previous classes. So there's different cases that can happen, but they can all be checked by seeing that there's no solution of the theta beta Mach number equation. Let's look at two more colored Schlieren now of the particular examples we're looking at. In the lower left, we see a particular flow at Mach 3 in air with a turning angle of approximately smaller than 50 degrees, because I think for this particular Mach number, the maximum theta for an attached shock is 50 degrees for gamma 1.4, according to the theta beta Mach number equation. So you can see on the left, we have the same incoming flow with the same properties, but of course this conic surface, which is a cone in this case with a sharp leading edge, has a very small turning angle, maybe about, I don't know, what is that, 30, 35, 40 degrees. And you can see indeed that we have an attached conic oblique shock. On the right, we can see that we have still the same supersonic flow in front of our device, but we've increased the turning angle to be greater than 50 degrees. That looks to be about 70. And of course, the shock wave itself detaches from the front of the cone, and we see this beautiful picture. And once again, we see many of the types of flow physics that we observed in the last two figures on 288, 282, and of course now in 383. How do we analyze these types of problems? Well, the detached shock case is way more complicated than the attached shock cases. And, of course, it's governed by the same set of equations, but with different boundary conditions. Here we've shown in figure 284 a particular schematic of the cylinder and crossflow. We see all the flow phenomena we've talked about in this class, except the turbulent wake, the turbulent boundary we've touched a little bit, and of course the expansion fans, which are coming next. We see once again a supersonic flow in front of the detached oblique shock. We have indeed a weak part of the solution far away from the body. We have a strong oblique shocks, and we have an incoming Mach number in 1. And of course, behind relatively the strong shocks and part of the weak shock front, depending on its local Mach number and wave angle, we'll have a subsonic condition behind the shock. Outside that region, we have supersonic flow, which is represented as indeed an expansion. And behind the cylinder, we have a turbulent wake. It is indeed a very beautiful flow. Unfortunately, to find and ascertain all these flow physics, we would need to use numerical methods, which of course we call today computational fluid dynamics. Indeed, there's no general analytical equations or even tables and charts to really easily find the flow field and associated aerodynamic properties of our vehicle in a simple way, like we're doing for, of course, the planar oblique shocks in this class. Now, in this particular flow field, it contains all types of flows that we're interested in studying. It contains very low-speed flows near the wall and the boundary layer. It contains transonic flows, especially near the sonic line. It contains subsonic flows in front of the vehicle, and supersonic flows around the vehicle and very much far in front of the vehicle in front of the shock. We can interpret these flows through a chart as shown in figure 282. In figure 282, we have basically a cone which is blunted by a radius, constant radius like spherical surface connected to a conic cone. And this is indeed the shape of many hypersonic type vehicles, which I'll show examples of in a few minutes. You'll see in this particular case that once again we have a shock wave, and we have supersonic velocity and velocity v infinity in front of it. We have the subsonic flow, and we have a supersonic flow as it reaccelerates around the vehicle. We've also drawn streamlines, and you can see that particular streamlines go through point A, B, C, C prime, D, and E. One of our homework problems is to study this figure and translate it into, of course, a different space, from a physical space into a graphed space. Let's try and consider also the standoff distance delta. Little delta might be the distance from the leading edge of the vehicle to the shock location. There are some papers, of course, which show these formulations, and one of our challenge homework problems is to find that ourselves. We might ask ourselves, how does A, B, C, C prime, D, and E translate into the theta beta Mach number charts or other types of charts? Let's look at this now for the particular detached shock problem. Here in figure 286 of this particular slide deck, I've shown the theta beta Mach number diagram where the x-axis is theta and the y-axis is beta. This is just like the traditional theta beta Mach number charts which we presented in this very class. So here we have one particular family of the solutions for a given constant Mach number m1. And you'll see I've labeled these values A, B, C, C prime, D, and E on the chart. And for a particular detached shock, the particular solutions might be viewed as dashed lines coming off, say, C and C prime and the other values. We'll look at C and C prime in particular. The first question we might ask is, how do these values map back to the actual flow field for the detached shock? Let's look at A. A is right here at theta 0 and some value of the wave angle, beta, which is actually 90 degrees. So theta 0 is a turning angle of 0, and beta is 90 degrees, which is the wave angle. Of course, that's right here at the normal shock location in front of the vehicle. Let's look at B. B is just along the curve, the family of curve for this particular Mach number, of theta beta Mach number equation. And you'll see this particular term, even though it's a detached shock, could be labeled as B for the incoming shock. Why is this? Of course, because we are in a strong shock region and we have subsonic flow behind the vehicle. or behind the shock, excuse me. Then there's points C and C prime. This is, of course, the transition from weak to strong shocks, and C prime, of course, is the weak shock transition point on the chart, where below this line we have supersonic flow everywhere below the dashed line. And you can see that, of course, on this particular figure as the sonic line here. Then we go to points D and E, which are very far away from the vehicle. You can see very, very, very far away from the vehicle, the shock becomes weak again and becomes a very, very, very weak normal shock. This would occur if it never hit the ground and just is so-called like dissipate in the atmosphere if it's a quiescent atmosphere. This rarely happens in reality, and shock waves from vehicles can travel at least 100 miles easily through a typical Mach 1.5 or Mach 2.0 type flows. So you can see it's a very strong situation. And the whole oblique shockwave family, even though it's a strong detached shock and not attached to the vehicle, can be translated to the theta beta Mach number curve as we showed in this particular diagram. In reality, for this particular incoming Mach number and turning angle of 90 degrees, we can see that, of course, there's nothing that falls on the chart, but we can interpret the actual shock wave and its properties across it with the same theta beta Mach number equation and diagrams. Why is that? Because, of course, we evaluated the differential element through control volume theory across the shock on the shock, not through necessarily the turning angle itself attached to a vehicle. This is one major advantage of the formulation we presented in this class and the physical understanding of the flow. Let's make some notes on the previous figure just to solidify it. Remember, point A is the normal shock. Point B is the oblique shock, which is strong, corresponding to the strong shock solution, right here. Point C, of course, will be the point dividing the strong shocks from the weak, where, of course, there's a singular solution of the theta beta Mach number equation, not 2 or 0. C prime is where the flow becomes sonic. That's the sonic point. So see, here's the sonic line, which is the dashed line, which is attached to the vehicle and moves up and attaches to the shock wave. And you can see that in the Schlieren. Point D and E, of course, are the weak shock solutions which go away from the wave, up in here, which we see that is D and E on the theta beta Mach number charts. Simple. So try and look at the chart, look at these notations, and look at the particular figure and see if you can make physical sense. You should be able to map any type of shock wave through this type of approach. Now let's turn our attention to three-dimensional shock waves. So far, we've really only considered two-dimensional oblique shock waves. But remember, even two-dimensional oblique shock waves are really three-dimensional planes. That is, it's a plane surface, which represents a discontinuity in the flow that's attached, perhaps, or detached in a particular vehicle. All shock waves, in reality, are, of course, three-dimensional phenomena in space and time, and they could even be moving. Now, in three-dimensional flows, the shock waves and their properties immediately after the shock can still be obtained with our approach through an approximation. It's not exact. What we might do is view the body, the front of the body here, moving through air, perhaps, from the lower right to the upper left, through this particular coordinate system, having a detached shock like we showed in the previous Schlieren. Now remember, the Schlieren images are three-dimensional, of course, but they're projected on a two-dimensional plane, which is why they're two-dimensional, and we view them as two-dimensional. But in reality, we're viewing a three-dimensional flow, which is like averaged through the density gradient light paths that approach the camera. Here, we can see a schematic of a three-dimensional shock surface in front of the body. So here's the front of the shock, perhaps. And then this surface represents maybe the side of the shock facing us, and the other side of the shock is not shown. And then we show this loop here just to denote that it's indeed three-dimensional. This is where we cut it off. In reality, of course, this bow shot goes to the upper right and lower left parts of the figure. We once again have a supersonic Mach number coming in, and locally, we might view, if this is at an angle of attack, the incoming Mach number from left to right, and our body's going at a large angle of attack, or yaw, relative to the incoming flow direction. This incoming Mach number might hit a differential element dA, with an outward porting normal defined from the outward normal of the shock as m1 into the vector location with normal vector out unit. So we might know from this a particular incoming Mach number and relative angle, even though it's not exact, based on the normal direction between the vector Mach number coming in and the normal vector. And so we know from this, perhaps we can analyze the wave angle and incoming Mach number and find the properties locally at each particular differential element across the shock itself. This is an approximation, remember, because we developed our theory for different types of shocks, but yet it's going to give us a good approximation. And so from this, we might define the normal Mach number. And we could write that the normal Mach number, mn1, goes as m1 in the, which is of course in the I direction, dotted with n. And therefore we get our normal component of Mach number, which we can then use and find quite easily our values after the shock through approximations of the static pressure, the static density, the static temperature, the static enthalpy, and mn2, which is the normal Mach number after the shock, which of course is going to be deflected relative to the incoming original flow direction. So for three-dimensional flow, the shock properties after the shock can be obtained with the approach, but just realize it's an approximation. In real three-dimensional flows, we have indeed developed more exact analytical relations for these types of shocks, but they do not have closed-form analytical solutions. They are instead tabulated in the famous Ames tables, which show the solutions. And once again, I've placed the Ames tables on our class website for you to download and examine. For example, you can handle these problems by taking the tables and doing table lookups. Or you could devise numerical methods and solve the equations numerically, which are also shown in the Ames tables, but not my particular equation sheet. This way you can at least approximate the values. In reality, these problems are typically today solved with full computational fluid dynamics solvers, which solve the full Navier-Stokes equations with appropriate boundary conditions. Let's now look at one particular table from the Ames tables, which I show here in figure 288 of this particular slide deck. Here the x-axis is the cone semi-vertex angle in degrees. So if you look at the little diagram here, if you can see that with the YouTube or video compression, whatever site this is on, you'll see that there's a half angle. So this is the turning angle. And there's actually multiple pages for this chart. This angle is from 26 degrees to 58 degrees for the half angle of a cone. A cone, not a wedge, which is 2D. A cone is three-dimensional and axisymmetric about its centerline axis. So this is a cone, conic, with a sharp leading edge. In fact, this couldn't be used to solve the particular problem like we see in figure 287 because, of course, we have a blunt leading edge. Nonetheless, the y-axis once again is deflection angle, and it goes from 0 to 90 degrees, and so they have 1 degree increments. In this particular case, you can see in the figure, they show that the y-axis is this angle from the centerline axis of the cone to the shock wave. And then there's an incoming Mach number. And for this family of solutions for the cone, for gamma 1.4, and there's different charts for different values of gamma, they show different values of incoming Mach number. This is 1.4. This is 1.5, and it goes all the way out to the asymptotic limit of m equals infinity. You can see there's very little change in high Mach numbers between Mach 20, 30, and infinity way out here. And so, of course, the curves are bounded in the theta beta Mach number solutions of the cone. Remember, the theta beta Mach number equation is not the same for, say, cones and wedges, and that's why we're getting different graphs. In fact, you can see there's no upper family of solutions for the theta beta Mach number equation. There's nothing plotted up there. We only have the classic family of weak solutions in the lower half part of the plane. This is curious, and it shows different mathematical properties of different equations, where the theta beta Mach number equation for, of course, two-dimensional flow over the wedge has multi-value solution, while the cone flow has only a singular solution for any given value of turning angle and wave angle for a particular Mach number. And so we don't have to worry about multiple solutions or deciding if it's an attached or detached shock. Now we can also have the cone flow where we have particular solutions where there's a particular turning angle and a particular Mach number where indeed we might have a detached flow. What might happen in that situation? Let's look at some particular cones. Remember, a cone can be placed at any angle of attack in the free stream as we showed in the previous diagrams, like this on 264, the Ames tables on 766 of the fly deck. And in this case, the flow field might be no longer axisymmetric. So if the angle of attack, or yaw, of the cone is 0, that means the cone is aligned exactly with the incoming flow. That is, the centerline axis of the cone, shown here, is exactly aligned with the incoming flow. Now, if we raise the angle of attack or lower it, or change the yaw angle in degrees of the vehicle, then of course the axis of the cone is no longer parallel with the incoming flow, and we can't use the classic tables which I just showed. In fact, there would be a whole other class of tables which will give us the solution as a function of azimuthal angle around the cone. Now here's some particular diagrams where we can see that indeed the flow field around the cone is now fully three-dimensional. It could have a single plane of symmetry if the cone is axisymmetric in an angle of attack, which would go from top to bottom with a plane of symmetry through the middle of the cone, extending down through the tip of the cone. Now, at large enough angles of attack, the flow becomes even more complicated. And indeed, there's different roll-up of vorticities. In this particular picture from Rainburn in 1968, from their article, you can see the cone has a sting, and here's the cone body, and wrapped around it is an attached conic oblique shock. In fact, now, in the boundary layers, there's large attached primary and secondary vorticities are rolling up and attached on the upper side of the cone, which is of course considered maybe on the suction side of it, as if it was an airfoil. Within there's particular shock waves which are even forming, and the flow becomes more complicated. This flow can be viewed from a zebra stripe Schlieren on the left. Here we see an interferogram of a cone in a free flight at only Mach 2 and an angle of attack of 37 degrees. This was published by Kovalev and Mende in St. Petersburg, Russia. You can see here's the cone outline, which you see on the right. And indeed, here's the zebra striping from top to bottom. That signifies the undisturbed flow. And here you can see the zebra striping has been bent, which is the oblique shock wave, which is attached to the front of the vehicle, even at 37 degrees and Mach 2. You can then see there's a boundary layer on both sides, and look at the strong distortion of the zebra striping, which corresponds to the density gradients effect with bending of light below the cone, right there. Up top you can see hidden in the flow and zebra striping, and we would not know about it from this particular experiment, these particular vorticity roll-ups. This is a case where of course the experiment has not shown all the flow physics. Once again, of course, there is this high-speed shear layer, which you see here with this strong angles of this zebra striping above and below the cone and a turbulent wake behind it. It's a beautiful picture and a very, very difficult problem to analyze that people are even doing research on today to understand and study. Let's look at some examples of these particular cones where you have attached conic oblique shocks. Some of these we've already looked at previously. In the upper left, we have the classic projectile moving from left to right, and here's a Schlieren image. I've described this so many times that I'll leave it for you to think about. In the upper right, we have a classic MERV system, which I'll talk about briefly on the next page. In the lower left, we have the classic arrow spike inlet, which was pushed forward in the MiG-21 aircraft. So here's a double turning angle arrow spike. And if you remember from our previous classes, you might remember why it's beneficial to have a system of oblique shock waves in the inlet versus a single normal shock. And on the right, we have the classic SR-71 arrow spike inlet, where, of course, an oblique conic shock wave attaches to the cone and it directly merges and hits the outside cowl of the vehicle, which we've shown schematics of earlier. So now you can see that really, for these conic cases, you cannot use 2D planar solutions at all. In fact, we do that in the class to illustrate the analytical concepts. In reality, you would of course have to use conic equations for theta beta Mach number curves to solve these problems. In reality, today a lot of people simply do computational fluid dynamics to try and capture these flow effects. But of course, CFD is very complicated, and you'll have to spend a lot of time to understand the physics and equations before you can solve them numerically. Here's one picture I took in Dayton, Ohio at the United States Air Force Research Lab. And this is one particular on display MERV system, which is a multiple independent reentry vehicle. This was mounted at the top within the nose cone of the LGM-118A Peacekeeper missile system. So each one of these, of course, separates on a ballistic trajectile above its target and re-enters the atmosphere. So there's actually 1, 2, 3, 4, 5, 6, 7, 8, really 9. I think one's put in the middle too, which is missing. Small, basically nuclear devices, which would separate to different targets. Now, let's examine the oblique shock relations in tables now in the class, now that we've studied, of course, the oblique shock wave theory. I encourage you to try and solve and evaluate the equations yourself. You can also use the tables. I highly recommend getting used to the tables and equations because, of course, that's what students might have to use on their midterm. You won't have the numerical system available to you. Now, recall, here's the compressible aerodynamics calculators. For the type of problems we've looked at, we'll need to use isentropic flow to discover the properties before and after the shock. To cross the shock wave, of course, we will need oblique shock relations. The oblique shock relations you see in the compressible aerodynamics calculator, which is available through the class website or online at Virginia Tech, will show an oblique shock relations category. In here, you can put gamma as 1.4 if you wish, or any other value, which is the ratio of specific heat, Cp over Cv. You'll also have an input Mach number, M1, that's the Mach number before the shock, and you can choose a turning angle, which would be weak or strong, and that would of course be in degrees. If we do an example and say Mach 1.6 and a turning angle of 4.5 and hit calculate, we'll have all the following properties across the shock. Notice the values of, say, PO2 over PO1, which is the total pressure loss ratio across the shock, is only 0.9988782. You can also automatically find all the other quantities which we spent a lot of time talking about in this particular class. I've also highlighted the interesting concept of the wave angle. This is indeed the wave angle beta. So for Mach 1.6, turning angle 4.5, I get a beta that is wave angle relative to the incoming flow direction of 43.51. Please take the time to try out this chart, and you can, numerical calculator, and you can of course use it to check your homework. And in practice, when you're doing some designs or even checking your CFD calculations, you can use this calculator to see if you are indeed correct. It's a little bit easier than, of course, doing chart lookups, and certainly more accurate if the numerical method is convergent. Let's now look at some charts, and I'll describe the charts I present in class and the AIMS charts in class one-on-one offline in the actual class, of course. So let's look at these particular charts from the AIMS tables, for example, and we'll do an example. So example 1. And remember, the x-axis is the deflection angle, and the y-axis is always the wave angle on these particular charts. And each line represents a contour or particular family of solutions given in a particular incoming Mach number M1. Here, indeed, we have the strong shocks above and the weak shocks below, and a range of weak shocks with M2 less than 1. Let's now try an example with particular incoming Mach number M1 and flow deflection angle 20 degrees and a gamma 1.4 flow. Remember, the charts are tabulated for specific gamma, and the charts I've given you in class are gamma 1.4. And we're asked to find a corresponding shock wave angle beta. So how do we do that? Well, we're going to enter our charts at theta 20 degrees, which is approximately right here where I've drawn this black line vertical across all theta 20 from top to bottom on the chart. Right there. Now, for M3, along the M3 curve, which goes like this, which right here, and right here, you'll have to look at that up on the chart with the right axis labels for the AIMS charts, you'll see that we indeed have two particular flow deflection angles by drawing a line where M1 equals 3 and theta is 20 degrees. Horizontally over to the left axis, and you'll find a value of 37.8 degrees and 32.2 degrees. Indeed, there's two solutions for this deflection angle and Mach number of the theta beta Mach number equations. So which one exists? Well, it depends on how the flow is started and, of course, what the back pressure is. Strong or weak shocks can form, of course, to match the particular back pressures or other boundary conditions in the flow, as we discussed in previous classes. Let's try an example of the opposite case. Here again, we have our particular charts for a wedge case. The example says, given an incoming Mach number M1 of 2.8 and a Mach number after the shock, oblique shock of 2.2, for gamma 1.4, we'll find the corresponding wedge angle theta. And indeed, there's other charts in the Ames tables which give you values of M1 and M2 and corresponding deflection angles, which of course is a solution of a particular equation we developed in this class. The family is the solutions for M1, M2 with particular deflection angles. So the solution is simple. We'll enter the chart in M2 of 2.2, which is on the left y-axis, right here, and then we'll read across and draw a horizontal line right there. Now we'll also draw and look for a particular point where we draw the horizontal line where it crosses M1. Each one of these lines represents the contour solutions or families of incoming Mach number solutions. And we would of course look up the incoming Mach number of 2.8, which is right here, which goes along this particular line. This line, which is M1, merges here where my cursor is moving for M2 2.2. We then draw a line which is vertical down the chart, and we find a point here, which of course is the deflection angle, the turning angle of the flow, which is indeed exactly, in this case, or very, very close to 13 degrees. So you see N1 and M2 across the oblique shock completely define the problem. And indeed, in this case, there's no strong solution in the particular example. On the other hand, if we took that 2.8 value and traced the other curve, we could also find an alternative value of M2, which is of course about right here. And that would have a value about 0.54. Try the case yourself for the strong shock. Now, you might ask yourself, how do I know whether I to use a solid or dashed line for strong shock or weak shock, respectively? Remember, the solid lines are for the weak shock waves, and the dashed lines are to warn you that you are indeed looking up a strong shock solution. You can always remember that the strong shock solutions are at the top of your chart, and, of course, they have corresponding greater decreases in Mach number, which, of course, are subsonic. So that's how I simply remember it. I don't worry about if the lines are dashed or solid. Now, these are all tabulated in the particular books published in 1964 from NASA Ames Research Center. This is a picture of the cover from my compressible flow professor, Gary Settles, when I was a graduate student. I have my own copy with my own name on it. Perhaps it's a little bit of a tradition that everybody have their own original copy if they work in the field of fluid dynamics and high-speed aerodynamics. Let's look at the particular tables, which we haven't yet, for the theta, beta, Mach number equations and oblique shocks. This value is indeed for gamma 1.4, and they're tabulated for Mach number. So at the top of the table, you'll see M1 equals 2.95. The particular Ames tables, for instance, will have many pages of these particular charts and tables for given M1 and gamma. And this is for very weak or weak shocks only. In the columns, we have our particular values, of course. We have the deflection angle in the first column, the wave angle in the second column, the Mach number after the oblique shock. We'll skip this column for now. And we'll have the pressure, density, and temperature rise across the shock. The ratios of P2 over P1, rho 2 over rho 1, and T2 over T1. And of course, we'll have ranges and losses of the total pressure, and we'll have a delta S, that's the entropy increase. So of course, with increasing deflection angle from basically 0 all the way up to high values, here it's 33.7275 degrees, we'll have corresponding wave angle of 65.19 degrees. And then you can see here's where we transition from supersonic flow after the shock to subsonic flow after the shock right here. And of course, all the pressure, density, and temperature rises will rise across with shock, as you see from decreasing and increasing wave angle values. And of course, you'll see that our total pressure goes down in the tables for each corresponding row, and we have an increasing delta S. And I've denoted these relations at the bottom of the figure, courtesy of Professor Gary Settles, actually. Now, at this particular point of the class, I would like you to go through this particular example yourself just to solidify all the points. It's one of the most simple examples between finding the flow between a 2D planar wedge with angle theta and a circular cone with angle theta, equivalent angles. Try and use, of course, the charts for each of these problems because you'll have to solve the theta beta Mach number equation. Here, the shock wave angle will be 36.9 degrees with respect to the incoming airflow, and the Mach number will be 2.6. You'll have gamma, which is 1.4. You'll have beta, which is given in M1. Try and find the particular wedge deflection angles for the wedge and the cone, respectively. I'll let you do this now, and then check your answers on the next page. In this class, we looked at the idea of shock detachment, of course, which happens when there's no solution of the theta beta Mach number equation for some given respectable boundary conditions. We then looked at the three-dimensional shock phenomena and its transition into the conic cone cases, and discussed how we might approximate solutions of our present theory. In reality, of course, we use computational fluid dynamics for these approaches. We then discussed and looked at briefly the Ames tables and how to do table lookups and chart lookups for theta beta Mach number equations, M1, M2 theta equations, and of course the famous Ames tables lookup based on incoming Mach number and gamma. You have all this material available on the class website, and I strongly suggest you take some time to get used to it. Thank you very much for your time today. I'm Professor Steve Miller.